me start by thanking the organizers for setting up this really wonderful meeting and inviting me to speak. I've been to Prague only once before, and it was for a high school graduation trip. And well, I guess because it was a high school graduation trip, I don't quite remember as much of Prague as I would have liked to. So it would have been really nice to come in person, but such are the times, and it's still great to be able to have this meeting on Zoom. And I guess it's also pretty great that Facebook doesn't own Zoom yet. So today I'm going to talk about some work that I'm really excited about, and my talk will be mostly based on one recent paper that came out this summer with Sean Cullen Ellerin, who's really an excellent grad student at UC Davis, and he's applying for postdocs this year, so definitely look out for his application. But along the way, I'll also mention some older work that came out a few years ago with Nabil Iqbal, Sagar Lakande, and Yorick Kurdov. And well, if that's okay with the organizers, let me start right away by contradicting them and saying, please do interrupt me and ask questions. It certainly doesn't disrupt the flow. On the contrary, I think it's very useful to give an informal environment. So please, if that's okay with organizers, don't hesitate and interrupt me more or less as much as you like. For sure. Great. So let me get started. I think it's fair to say that using insights from quantum information theory has really given us like a new mindset to probe quantum gravity. And all these developments have been happening for the past, say, 15 years and are really exciting. And sort of the star player in this whole program is the Ryo-Takenagi formula, or its quantum generalizations, which you can view as a generalization of the Bekenstein-Hawking formula to compute the entropy of black holes, this time applied to CFT subregions. And what this formula says is, if you want to compute the entanglement entropy of some subregion A, how do you do that in the bulk? Well, you consider the area of some minimal surface that extends into the bulk over 4G Newton. And you add to that the entanglement entropy of all fluctuating fields that sit between the minimal surface and the surface gamma and the boundary region A. And then you extremize over all possible surfaces gamma of this type. So here's a cartoon for this. I'm sure you're all familiar with this, but let me still summarize it nonetheless. So you have some CFT region A, and you look for all possible surfaces that extend into the bulk and that finish at the boundary of A. And then the thing that you're supposed to extremize is the area of that surface plus the entanglement entropy of all fluctuating fields. So, it could be gravitons, scalar fields, gauge fields. You compute their entanglement entropy through the surface, and then you extremize this combination. Okay, and this was first formulated at the classical level by Ryo-Takenagi and then generalized to include quantum corrections in a whole series of papers. And of course, I haven't indicated all of them here. This formula, you can derive it.
Since you invited us to interrupt you.
Please do.
I had a question.
Yes.
So I wanted you to see if there was any comments on the fact that this surface, from the bulk perspective, requires, is there a clash of diffeomorphism invariance from the bulk perspective as to where the location of the surface is? And in parallel to this question, there's a question of the fact that usually the dual theories are gauge theories, and gauge theories have certain ambiguities when it comes to defining entanglement entropy because it's difficult to split point-wise the Hilbert space.
Yeah.
Is the situation, I just wanted to see whether there was an update on the thought of this kind of issues.
Right. So concerning diffeomorphism invariance in the bulk, this formula here is diffeomorphism invariant because it's specified. It's specified in two ways. One's from its boundary conditions. So we're always allowed to fix points at the boundary. That's okay. That's one part of the data. And the other part of the data is just extremality, which is a diffeomorphism invariant quantity. If you want, you can define it, for example, as trace of extrinsic curvature is 0. And that's a scalar equation, which is diff invariant. So the location of the surface is specified in a gauge invariant way. And then the second question is a bit more subtle about the fact that the boundary theory is a gauge theory. And so there's a bit of an, first of all, I'll come to this in a second, but entanglement entropy is UV divergent. And then there's an ambiguity exactly with what you do at the entangling surface in a gauge theory. Maybe I'll just come back to that. If you can give me 5 minutes, I'll come back to that question in a second. And I think you can define quantities that don't suffer from any of these ambiguities, and in which case everything is fine. But thanks. Good. So this formula this master formula that I showed you on the previous slide, it can be derived from the semi-classical gravitational path integral using the replica trick. And this was first done in a paper by Lefkovich and Maldacena, and then revisited more recently in the context of these replica wormholes and the island formula. And the idea is always the same. You do the replica trick on the boundary, and then you look for a gravitational solution that fills in the bulk. And then you still need to do an analytic continuation to obtain the entanglement entropy. And there's a way that you can quotient by the ZN symmetry, the ZN replica symmetry to find, to have a sort of convenient way to do the analytic continuation, and then essentially derive the formula on the previous page. And the new insight, as Tom reviewed yesterday, is that this formula is enough to produce a unitary page curve. So if you try to compute the entropy of the Hawking radiation as a function of time, it starts increasing, and what Hawking's calculation tells you is that it increases forever. But if you use this quantum Ryotake-Nagy formula along with the island rule, what you can show is actually it goes back down, and you find a curve that's compatible with unitarity. So the conclusion that we seem to get from this is that, well, we can see avatars of unitarity just from semi-classics. It's maybe not the full unitarity. We haven't proven the unitarity of the S matrix. That's a lot more than just the page curve. But we certainly see avatars of unitarity just from the semi-classical, computation. And as it appears to be, there's no need for the full microscopic details. We don't need all the strings, the brains, etc. And I would say that, that's both exciting and disappointing at the same time. It's exciting because it's telling us that somehow the low energy effective field theory knows a lot more than what we previously knew. But it's also disappointing because, as string theorists, maybe we would have liked there to be, that the strings and the brains and all the microscopic details are important for the resolution of the information paradox. And perhaps they still are, but at least for these avatars of unitarity, like the page curve, they don't seem to be. So this immediately raises two questions. Well, if the full microscopic details of the CFT are not needed, you can ask, well, exactly how much of it do you need, to see these avatars of unitarity? And then a second question, which is really going to be the one that I'll try to be addressing today, is, well, say you identify exactly how much of the CFT is needed, then you can ask how does the microscopic degrees of freedom, or maybe the subset of the microscopic degrees of freedom that you need, how do they get reorganized and reshuffled into this Ryotake-Nagy formula, into this generalized entropy? Okay, and this is really what I'm going to try to address today. So my goal will be to present a dictionary, and it's going to be a dictionary between, microscopic CFT data and pieces of this quantum Ryotake-Nagy formula, or pieces of geometric pieces related to these quantum extremal surfaces. And ideally, what I'd like to do is be able to tell you how all of this works in the context of a black hole evaporation that you couple to a bath, and in some high energy process of that type. But for today, I'll have a less ambitious goal. I'll restrict to the low energy sector of the theory, or to the perturbative sector of the theory on top of the vacuum ADS. And in that context, we can hope to make this dictionary precise or sharp. Okay, and from what Tom told us yesterday, I think it's pretty clear that if you go to high energy, the part of the CFT that is needed is maybe not the full microscopics, but maybe the statistics of the microscopics. But that's a much harder question. And for today, the goal will be less ambitious, and I'll restrict to the low energy sector. But I'll try to convince you that this dictionary can be made precise. Okay, so before I get to that, there's some important subtleties. And this is where I'm going to come back to Dio's question. So there's two subtleties. The first one is that the CFT is UV divergent. The entanglement entropy in the CFT is UV divergent. And this comes from the entanglement of, we have a continuous quantum field theory, and this comes from the entanglement of degrees of freedom very close to the entanglement surface. This is a known problem and has been known for a long time. It gets even worse in gauge theories because there's an ambiguity in defining, algebra of observables. But at the end of the day, this is not really a problem because you can always define quantities in the CFT that remove this UV divergence and all the ambiguities that go with it. And so there's various quantities of this type. You can consider the difference of entanglement entropy between two states, like an excited state in the vacuum. Maybe even better, you can consider the relative entropy that has nice positivity properties, or the mutual information. And the list really goes on. There's many more quantities that you can consider where this UV divergence is simply not present, and they're completely regular. So this is a
sorry, Alex, just to understand the claim. So
yes.
You're saying these are choices analogous to what people talk about in the entanglement entropy literature, the electric center or the magnetic choice. When you declare that it's a problem, picking one of these choices people make when compute entanglement entropy in H theory, you say that they're completely insensitive to this. Because I thought what you mean by finite part of the entanglement entropy might be sensitive to how you cut the links and what center of the algebra you choose.
Well, as far as I understand, these sort of discrepancies that depend on the choice of boundary condition that you impose, they can affect terms that are UV divergent, and for example, they can even affect log terms, say in 4 dimensions, that are very universal and know about anomaly coefficients.
I think it claims, okay, I'll stop it now, but I think it's even the finite part. For example, in the topological entanglement entropy literature, it's even the finite part that is discussed as depending on these kind of choices. But we can talk about this later. I've just been
okay, yeah, you should tell me more about this. I thought that anything that would appear here is not sensitive to that. But yeah, we should definitely discuss it more.
Thank you.
On GatherTown, and we should all go on GatherTown. Let me just advertise it. It'll make the organizers happy. Great. Thank you. So GatherTown is also very dear to my heart for historical reasons. But okay, there's a second subtlety which is much more serious. And this is the second subtlety is that there's bulk UV divergences, right? We're computing a bulk entanglement entropy through a surface, and that's UV divergent in the bulk. Now, the general lore on how to deal with this is that, well, really, you compute S bulk and there's UV divergences, but these UV divergences, they get reabsorbed into G Newton. And they get reabsorbed into the renormalization or the running of G Newton. And that's another reason why you should think that it's kind of very natural that these two objects appear together and that they don't really make sense independently at the quantum level, because just by running the bulk RG, you can shift contributions from S bulk to A or from A to S bulk, depending if you're going up or down the RG. And it's also been shown that, by doing field redefinitions in the bulk, at least in 2-dimensional contexts, you can also shift contributions one way or another. So at the end of the day, the CFT is computing some unambiguous quantity. And so it's natural that the thing that you compute is not sensitive to any of these subtleties. And so it is only really the sum of these two terms. So this is the general lore, but this should, of course, already worry you about the program that I'm trying to implement, which is trying to tell you, given some CFT microscopic piece, how does it get geometrized? Does it go here or does it go here? And you might worry that because of these subtleties, the question that I'm trying to ask doesn't really even make sense in the first place. And maybe one of the surprises that comes out of what we did is that there seems to be unambiguous ways to associate certain microscopic terms to the area or to the bulk entanglement entropy. Okay, but I'll come back to that during the body of the talk. So let me just give you a sketch of the dictionary before I go and try to convince you that this is how it works. So like I said, I'm going to consider a CFT state that is a low energy state and is obtained just by acting with a single trace operator on the vacuum. And the relevant pieces of the microscopics, the relevant building blocks of the CFT that you need to compute the entanglement entropy, I'll show you how very shortly, but I just want to give you a sketch, is, all the single trace operators of the theory. So say the one you use to create the state. In all theories, there's going to be a stress tensor. And then there's a bunch of multi-trace operators. Here I've written down the double trace operators. And these multi-trace operators have their own microscopic data. For example, their conformal dimension is given by sort of the infinite C or generalized free fields conformal dimension, plus an anomalous dimension that appears due to 1/c corrections. And similarly, the OPE coefficients, they're given by just the generalized free field answer, which is just Wick contractions, plus a correction that comes again from 1/c effects. Okay, so these are sort of the building blocks, and the question is, how do they assemble into the generalized entropy in the bulk? And so here's how the dictionary looks like. Here's what it looks like. We have a CFT entanglement entropy, and it has various contributions coming from the identity operator, from double trace operators. And then order C to the 0, this was already understood in a previous paper with Nabil and Sagar. We understand that the identity operator gets mapped directly to the area operator in the bulk, and that the bulk entanglement entropy is responsible for these double trace exchanges. And there's sort of additional subtleties, is that there's kind of cancellations between these two terms that appear on top of this, and I'll come back to that in the body of the talk. And what I want to focus on today is the next order in the 1/c expansion, and going to the next order is really important because that's the order at which quantum extremality becomes relevant. So if you want to probe, really quantum extremal surface, you have to focus on this order. And the part that I'll try to convince you of today is that if you now go to this order and you look at the contribution now no longer of just the identity operator, but also the exchange of the stress tensor, that this is fully captured by the area operator. And then there's these other pieces, these anomalous dimensions to the double trace operators and their OPE coefficients. And this part of the dictionary is still being constructed. We're working on it. I can't tell you exactly how it works. But what I'll try to convince you is that at least this part of the dictionary is clear. And there's another very interesting question that I'll have nothing to say about today, but I think is very interesting, is to study not 1/c corrections, but 1/delta gap corrections in the CFT, which in the bulk dual map to string theory effects. And there's a proposal for how to deal with higher curvature corrections to RT, but not what we're supposed to do if the gravity dual is really string theory. And so it would be really interesting to understand what these stringy effects map to in the bulk here. But this is beyond the scope of the talk today. But I think it's an interesting question to keep in mind and can be sort of embedded in this program. Okay, so what's the plan for today? Well, this was my introduction. I'll go through first the CFT computation, then turn to the gravitational computation, and finish with some conclusion and open questions. But before I dive in, maybe are there any questions?
Yeah, I have a question.
Yes.
So you and Dio mentioned that splitting of the CFT into like entanglement areas is particularly difficult for gauge theories. But I guess you could just like define something, some box space from some simple operators, and why can't I just take traces of powers of the stress tensor? Of the, field strength tensor?
Yes, so indeed, I mean, so when you define an algebra of observables, it's going to include things like what you just said, which are, say trace f to any power or something like that, right? So that will be local operators, but the problem is that there's also other degrees of freedom in your theory Say, you know, a local operator in one region, a local operator in another region, and then a Wilson line that connects the two, for example, right? And these are degrees of freedom that, you know, cross through the entangling surface. And the question is how you deal with those. So I would say that sort of the local operator part of what you said is pretty obvious, but then there's really, you know, some extra subtlety on how you deal with gauge fields through the entangling surface. And you can even see that, you know, if you go to the lattice, even on the lattice, you can see that, you know, there's like links that go through it, and those are subtle. And so, well, I think one way to say it is that, you know, you need to define an algebra of an operator algebra, and there's multiple choices of operator algebras. And that's really one way to think about them, say, you know, in free Maxwell theory is about this electric or magnetic choices through the entanglement surface.
Right. Thanks. And I just noticed that Dio in the chat put like a reference, so I'll check that out. Thanks.
Okay. Thanks, Dio. Great. Any other questions? Okay. If not, let me dive in. So the CFT computation, for the rest of this talk, I'll focus on ADS3 CFT2. For most of what I say about the CFT part, being in 2 dimensions is not particularly special. There's a way to do similar computations in higher dimensions. For the bulk story, being an ADS will be special, and I'll come back to that in due time. But so I'll consider a state in a 2-dimensional conformal field theory that is obtained by acting with a single trace operator at the center on the vacuum. And for simplicity, I'll just consider a scalar operator. So, you know, its left moving weight will be equal to its right moving weight. And I'll consider the CFT on a circle, and my region A will be a part of a fraction of the circle, the interval 0 to theta. And in a very nice paper from, I guess, by now maybe almost 10 years ago, by Alcaraz, Berganza, and Sierra, they showed that the Renyi entropy, or the difference of Renyi entropies between the excited state and the vacuum, is given by this formula here. So it has some prefactors that depend on the Renyi parameter n and the size of the interval and the weight of the operator that you use to create the state. And it's given by a 2 endpoint correlation function, where the kinematics of the 2 endpoint correlation function are as follows. All operators are inserted on the unit circle, and they're grouped together pairwise, and they're separated by a distance theta over n. Okay, so here, for example, this picture would be what it looks like for the 4th Renyi. And there's multiple ways to see how you arrive at this formula. You can think about you know, the Renyi entropy as being a 4-point function between 2 twist operators and 2 operators that create the state. And because there's n copies, you have to you know, you have to put n operators. And then when you do a uniformization map, you get rid of the twist operators, and you're left just with 2 n operators living on the plane in this particular kinematics. So this is a formula that is true, you know, for any primary operator in a 2D CFT. There's no large C or anything like that here. But of course, what large C buys you is that then you can actually compute this correlation function. And for example, at infinite C, if O is a single trace operator, the only thing that you would get are all the possible weight contractions between the operators. And so you could just compute the Renyi entropy for any n. There is, however, a complication, which comes from the fact that we want to compute the entanglement entropy, not the Renyi entropy. So we need to do an analytic continuation to n goes to 1. And in general, that's difficult. But what you can do is you can expand this correlation function in an OPE expansion. So this is valid when theta goes to 0. So when these 2 points come very close to one another, you can do an OPE expansion. And then you can analytically continue the terms in the OPE expansion order by order. Okay, and that's the sort of most convenient way to compute this correlation function. So what do you get? If you just look at infinite C, so order C to the 0, you get 2 terms. The first term just comes from the identity contribution to this 2 endpoint function. And then you get a second term, which comes from the exchange of the operator O squared. Okay, so if I go back here, these 2, so here there's an operator O, there's an operator O, and they can fuse to give an operator O squared. and then maybe contract with this one here. And if you take into account all those contributions, you get the second term. Okay, so that's what happens at order c to the 0. And now you can ask, well, how does this get corrected at order 1 over c? And now there's multiple things that you need to keep in mind. The first thing, and this is going to be a bit peculiar for people that are used to the large N bootstrap, is that the single trace operator that we use to create the state itself could have an anomalous dimension. Maybe its scaling dimension is not exact in C. And so maybe really its weight should be given by H plus a correction that is suppressed by 1 over C. And that will give a 1 over C contribution to the answer. The second thing that can happen at this order is the exchange of the stress tensor, actually both T and T bar. That's also a 1 over C effect. Finally, there's the changes to the theta of the double trace operators. The first is that the double trace operator can acquire an anomalous dimension due to 1 over C effects. Of course, it'll pick up whatever change in the single trace operator there is at 1 over C, plus it can have its own anomalous dimension. And in fact, the exchange of the stress tensor and crossing symmetry implies that there's a non-trivial anomalous dimension to this double trace operator. And similarly, the OPE coefficient between two single trace operators and a double trace operator can get corrected by 1 over C. Okay, so all of these things can appear. All of these things will affect the CFT answer at this order. And like I just said, crossing symmetry completely fixes the form of the anomalous dimension, gamma 0, 0 and A 0, 0. And this was worked out in a nice paper by Collier et al. However, this correction to the single trace scaling dimension, this is not fixed by crossing symmetry. So this is just something that can appear. It's a free parameter in the theory. We need to fix it. And I'll discuss a little bit what happens to this in the bulk, and as it's slightly subtle and maybe a bit unusual from the large and bootstrap perspective. Okay, so these are all of the things that can appear. There's a list, there's 4 of them, and you can just go ahead and compute the change in the CFT entanglement entropy. And here's what it looks like. So you have all these terms that appear. This is basically the contribution of this term proportional to the change of the anomalous dimension of the single trace operator. This is the exchange of the stress tensor and T bar. These terms here come from the anomalous dimension of the double trace operator, and this term comes from the change in the OPE coefficient. And like I told you, they're fixed by crossing, so they just have particular values that I placed. And like I told you, I'm not going to give you the full dictionary of how everything gets reorganized into the bulk, but what I'll do for today is focus on one particular piece. It's going to be the first line here. And I'm going to ask, how does this piece get reproduced into the bulk? And again, I'll remind you, this comes from the identity exchange and the stress tensor exchange. And there's really a non-ambiguous way to split this line from the other two, is that the first line has only, in the OPE expansion, contains only even powers of theta, which is the interval size, whereas all the other terms contain powers of theta that depend on h, theta to the something h. And so that gives us an unambiguous way, by keeping track of the h dependence, this gives us an unambiguous way to split the two terms. Okay, so the goal for the rest of the talk is to try to understand, how does this term get reorganized into the bulk? Good. So that was the CFT part of the calculation. I went over it kind of fast, but are there any questions? Perfect. If not, let me turn to the bulk. So I told you that the CFT state is obtained by acting with a single trace operator on the vacuum. So you can ask, what is the bulk dual statement of that? And the bulk state, this is probably not going to surprise you, is just obtained by acting on the bulk vacuum with a creation operator for the field phi that's dual to O. Okay, so our bulk state is just basically a one particle state of the quantum fields that fluctuate in the bulk. So now if you want to study the generalized entropy at order c to the 0, which is order g nun to the 0 in the bulk, there's two effects that you need to keep track of. The first one is that the geometry is going to change. If you compute the expectation value of the bulk stress tensor in this one particle state, it's gonna be non-zero. Here's a cartoon of what it looks like. If you look at, say, the expectation value of the TT component of the bulk stress tensor, this is the radial direction, and there's going to be some lump of matter that sits at the center of ADS. And how peaked this lump of matter is depends on the mass of the scalar field or the weight of the dual operator. And so the heavier the scalar field, the more concentrated this lump of matter is going to be around the center of ADS. But once you have a non-zero expectation value for the stress tensor, you need to go and solve Einstein's equation, right? So you need to solve Einstein's equation, say, to linear order. So you expand the metric around the ADS metric, and you go and solve for the first order change in the metric. And I should say that at this order, there's no need to solve for the location of the surface, because since the surface is extremal, any first order change to the background will not change extremality properties of gamma. So at this order, all you need to worry about is the change in the metric, and then you just evaluate the old surface on the new geometry. So what does it look like? It's so simple that I can write it in a few lines. Here's our ansatz for the metric. If I just set these functions G1 and G2 to be 1, then it's just a global ADS metric. And then, so this is just a global ADS metric. And then there's a small correction. Remember, H is some order 1 number. So there's a small G-nun correction that corrects that. And it takes this very simple form for these two functions. Okay, and if I only look at the constant piece of G1 and G2, if I forget about this term for a second, you may recognize this. This is just a conical defect metric in ADS. But a conical defect metric is not smooth at the origin. And so the way you should view this metric is that it's a smoothened conical defect. And it's smoothened by the quantum nature of the particle that we're doing in the bulk. So, this peak is not infinitely localized. It has some spread due to the Compton, wavelength of the particle. And that's what's regularizing the conical defects. And another way to think about this state is that it's just a gravitational dressing of the one particle state in the bulk. Okay, the second thing that happens is that the change in the state also polarizes the bulk entanglement entropy. So here's the easiest way to see this. When you act with a global creation operator on the vacuum, you can also do a change of basis and go to Rindler creation and annihilation modes. And this appears with particular Bogoliubov coefficients here. And what I'm sure all of you know is that, this is also true in Minkowski space, is that if you take, the global vacuum and you trace over, say, the right Windler wedge, the state that you obtain is just a thermal state on the left Windler wedge. What happens is that when you act now with the creation operator on the vacuum, you change the state a little bit, which means that once you trace over the right region, you will no longer just get the thermal state, but you get the thermal state modified by an operator O and O dagger on each side. And O is basically just this operator here. So this is no longer exactly the thermal state. It's still very close to being the thermal state, but it just polarizes the occupation numbers by a little bit. And this is a very explicit expression for the reduced density matrix. So you can just go ahead and compute, trace of rho log rho, okay, at least in the small interval expansion. And there's something important here is that we're computing a difference between the CFT entanglement entropy. So we should also compute a difference in the bulk. And it turns out that the difference between the bulk entanglement entropy in the state psi and the bulk entanglement entropy in the vacuum is UV finite. So you just get a finite number, and there's no need for it to have any UV divergences in the bulk. Okay. And so what does the answer look like? Well, you compute the change in the area operator, you get 2 terms. You compute the change in the bulk entanglement entropy. Again, it's finite, you get 2 terms. And you can notice that actually there's 2 terms that exactly cancel against each other. And what you're left with when you look at this, you probably don't recognize it anymore, but it's exactly the order C to the 0 piece of the CFT entanglement entropy that I wrote before. And remember that this came from the exchange of the identity operator, and this came from the exchange of the double trace operator. So here we can really, associate a particular piece of the CFT to a particular term in the bulk, namely the area operator. We see that there's an extra subtlety, is that there's some extra term that appears in a way exactly to cancel between the area operator and the bulk entanglement entropy. And this happens here due to a first law of entanglement entropy in the bulk. But we'll come back to these cancellations later in the discussion, and I think it's kind of interesting to understand if there's a general understanding for them. But okay, so this was the order C to the 0, and these were all details that we figured out with Nabil and Sagar a few years ago. But like I said, this is at the level where we just have free propagating fields on top of ADS. The location of the entangling surface doesn't change, and so you're really not probing quantum extremality. So at order G Newton, we have to proceed to the next order. And I should really say that this is the order where things get murky. And maybe to some of you, it's well understood. You understand well what it means to do semi-classical gravity order by order in the G Newton expansion, but I find it to be pretty confusing. And so we were really here also just trying to understand, like in some sense, the devil's in the details here. And so what is meant by this quantum Ryo-Takenagi formula at this order becomes a bit murky. And so can we make sense of it? So this is what we tried to do. So what you should do is that, you should take your metric and you should expand it order by order in G Newton. You should take the location of your quantum extremal surface and again, expand it order by order in G Newton. And then you can ask, what are all the terms that contribute at order G Newton? Okay, and so there's 4 of them that you can write down, actually 5, but 1 will not contribute. The first one is just, you take the location of the old extremal surface, but you take into account the second order change in the metric. There's going to be, cross terms between the first order variation of the surface and the first order metric. There's going to be terms that are proportional to the first order change in the surface squared. And there's going to be a term proportional to the old location of the surface, but the first order change in the metric squared. And this is a piece that we can already compute because we had G1. I showed it to you on the previous slide. So, okay, this is some piece that we already know how to compute. And there's a 5th term that I didn't write down, which would be, the contribution to the second order change in the metric on the undeformed background. But again, this by extremality, this looks like just a linearized fluctuation for the surface for the location gamma 2, and by extremality, this vanishes. Okay, so we still have these 3 pieces to compute. And the missing piece of the data is how to compute the second order change in the metric and the first order change in the location of the surface. These are the things that we need to compute. So how do we find a second order change in the metric? Well, we need to go and solve for the bulk theory again, but this time to second order. Meaning that before we had, a free Klein-Gordon field propagating on vacuum ADS. And now what we need to do is solve for the Klein-Gordon equation for the scalar field, no longer propagating on vacuum ADS, but actually propagating on this corrected metric. So just like before, you expand the scalar field in mode and you try to solve for these wave functions. And so you find the undeformed ADS function plus a correction. And it turns out that we could actually solve for the Klein-Gordon equation analytically and find the expression for F1. I'm not going to write it down for you here. I do have an ugly equation on a later slide for the change in the metric, but it's some horrible function involving hypergeometric 3f2 functions. Okay, but it's a known analytic function. And what it looks like near the ADS boundary is actually has a nice interpretation, is that you just get the usual fall off, 1 over r to the delta that you're all used to in ADS CFT, plus a correction that looks like r to the 3 delta. And this is really, you can think about it as the stress tensor near the boundary falls off like 1 over r to the 2 delta because it's quadratic in the scalar field, and so that's just correcting the wave function in this sort of expected way. Great. So to find the second order change in the metric, we do just like before. We compute the expectation value of the first order stress tensor this time, and now we solve for G2.
Sorry to interrupt, but
yes.
We started a little later. Nevertheless, we're nearing the end of those 45 minutes. So just to
Yes.
let you know that
I'm keeping
like 5
track of
minutes.
time.
Cool.
Yes.
Okay. Thank you.
Thank you. Okay, so you can solve for the metric in the same way that we did at first order. The expressions get even messier, and this is really where Sean's bravery was very impressive. But we were able to find an analytic formula for the second change in the metric. So remember, there was these functions g, and this is just what the second order change in the metric is. Okay, and using this metric, you can go ahead and compute the change in the area due to the second order back reaction. And again, it's obviously not clear from this formula, but this formula, this metric is smooth at the origin. So the way you should really interpret this formula is, again, as a smooth conical defect, but this time it's dressed to second order in the gravitational dressing around it. But there's one subtlety that appears, and it's related to this anomalous dimension of the single trace operator, is that once you have this metric, you can just compute the ADM mass and ask how much energy is there in my state. And you find this formula here. Okay, and so this is sort of, if you want, the classical energy of the single particle state, and it gets a correction due to, self-gravitation, basically. Now, you'll see that if you try to just associate that to a CFT state that's a primary operator with no correction, you'll just get a mismatch, because the energy of the state, if you say that it's fixed to all orders in 1/c to be 2 times h, then you'll be off by this factor here. But also, of course, you can say, okay, well, what I'll do is I'll introduce a correction that I'll put equal to this factor here. But now this is puzzling from the bootstrap perspective, because remember, I told you that the anomalous dimension of the single trace operator is not fixed by anything. It shouldn't be fixed by the bulk theory. It's a free parameter, and we should be able to tune it to be whatever we want. So you can ask, how is that compatible with what we found here, which is a definite value? And it's compatible in the following ways: that there's another parameter that we didn't change in the bulk, but that we could have, is the mass. And changing the mass by a small amount would also produce its own delta H. So the thing that you need to do to sort of just agree on the duality between the bulk and the CFT before you even talk about entanglement or anything else is that you better make sure that the energy of your states match. So what you do is you fix a value of the single trace anomalous dimension. Then in the bulk, you compute what you get by self-gravitation, and you tune the mass to be, the change in the mass to be whatever you want to fix for this delta H. Okay. And again, this is slightly unconventional from the large N bootstrap perspective, but it just seems to be what we're supposed to do here. And so without loss of generality, what I can do is just say that the mass doesn't change at all, and just I'll restrict to the case where this directly equals to that. But of course, if I wanted anything else, I could just perform a change in the mass, and then I would get a matching as well. Okay, good. So I have 3 minutes left. So let me go over this kind of fast. Now we can ask, how do we find the change in the location of the quantum extremal surface? And this is easier to do if you go to ADS Rindler coordinates that cover, only one Rindler patch. So these are the ADS Rindler coordinates. And like I said, the metric gets corrected at first order. So there's also going to be a change in the metric on top of Rindler. It's ugly in Rindler coordinates, so I'm not writing it down, but do notice that in here. And the nice thing about these Rindler coordinates is that the classical extremal surface just sits at rho equals to 0. Which means that the quantum extremal surface will be a small distance away from it, and so you can just expand it in the following way. And then the area functional, as a function of some general surface, rho 1 of x, takes the following form. And again, all these terms here, they're a bit complicated, but we know them explicitly. But remember that to find the quantum extremal surface, you don't just extremize the area, you also have to extremize the bulk entanglement entropy. But it turns out there's a nice way to do this, because if you just move the entangling surface by a little bit, this is known as a shape variation of entanglement entropy. And people have computed this, say in QFT and flat space quite a bit. And there is a sort of a universal formula for it, is that the bulk entanglement entropy will give you, a term that's linear in this change of the metric, times the coefficient, which is given by a 2-point function between the stress tensor and the modular Hamiltonian. And here, these are really bulk operators. This is the bulk stress tensor and the bulk modular Hamiltonian. Okay, and so now using this general functional, you can just look at the equation of motion for this shape variation, and you get this very simple equation. Okay, it's an inhomogeneous equation. The homogeneous part of it is super simple. It's just solved by an exponential. And then you just need to solve for the inhomogeneous part. But the inhomogeneous part completely splits. There's a geometric piece coming from the first order change in the metric. And there's a piece that depends on the bulk entanglement entropy. And we cannot compute this yet. We're working on it because computing this 2-point function is a little bit hard, but we can still estimate how big it is as a function of theta. And the point is that it grows like theta to the 4h. And like I told you at the very beginning, I'm only going to focus on terms that have even powers of theta. So for those terms, you can sort of drop this term completely and just focus on the first part. And this is sort of this weird behavior that somehow, you need to extremize both the bulk entanglement entropy and the metric, the location of the surface, but you do it in a way that sort of splits or factorizes. Okay, and so you can define, some sort of geometric part of the location of the surface and solve for that equation. And again, it's ugly. This is the last, I think, ugly expression that I'll show you, or maybe the second to last. But it's some definite analytic function that you can just solve for. And this is the location of the surface, how it's moved compared to the classical extremal surface. Okay, so putting all the pieces together, you go ahead and compute the area operator at order g unit. And what you find, again, keeping only the terms that have even powers of theta, is the following expression. And when you plug in what this term is, this is as a function of delta h, you get the following expression that exactly matches with the CFT computation, or at least the part of the CFT computation that's sensitive to the identity and the stress tensor. Okay, so just to summarize, what I did is I presented the first steps of a dictionary that is relating the microscopic CFT data, dimensions and OPE coefficients of the light operators of the theory to properties of quantum extremal surface. One can view this as a partial check of the quantum RT formula or the quantum extremal surface formula at an order where quantum extremality is important, and it's a partial check because we haven't yet computed the bulk entanglement entropy. But I'd say that I think it's the only partial check we have of this formula for gravity in more than 2 dimensions, where really there's the location of a surface to solve for. And at this order, what we showed is that the Virasoro identity block, in this case, it's just 2 operators, the identity plus the stress tensor, seems to be completely captured by the area operator. Of course, there's a lot more stuff in the area operator, and there's a question of how that's going to cancel against pieces from the bulk entanglement entropy, but that's for future work. So the open questions, obviously, the first one is just to compute S bulk and to finish these missing pieces in the dictionary that I told you about, and this is something that we're working on right now. Another interesting question is the question of boundary gravitons. So you might have asked, well, at this order, you're supposed to keep track of all fluctuating bulk fields and the gravitons coupled to the scalar field. So why did you not take into account the entanglement of boundary gravitons through the entangling surface? And the answer is that we don't know for sure. We don't think that we need their contribution, and we think they're only relevant if you look at states that are Virasoro descendants of some other operator. But for any primary excitations, we think that because boundary gravitons are topological, they're not really relevant to capture what's happening here. But to really answer this question, we'll need to really compute this fully and see if we get a matching. There's another interesting question, which is bulk cancellations. Even at order c to the 0, where it's just free fields on ADS, we seem to see that there's terms that cancel between A over 4G and between S bulk. And this is a bit puzzling because you could ask, do these terms really have physical meaning? Because if they cancel between 2 pieces, and you might want to say everything that's physical should be captured by the CFT. Here, there seems to be pieces that they do appear at intermediate steps of the bulk calculation, but they seem to cancel. So you can ask, what do they really mean, or how would one extract these individual pieces that cancel? It seems to do that, you would want to isolate the area operator, but we know that that's not a good thing to do. So I think that's an interesting question, but I don't have too much to say about it. And finally, there's the question of, can we really distill contributions that go to the bulk entanglement entropy with respect to those that go to the area operator? And will we be able to get an unambiguous dictionary, say, to all orders in the 1/c expansion? And well, the short answer is I don't know, and I think it would be interesting to check. So I think I'm over time, so let me stop here, and thank you very much for your attention.
Okay, thanks, Alex, for a very clear and interesting talk. Let's move to the question part. We have a couple minutes, so if there's questions, please do ask.
Yeah, sorry, I have a question. In your main result on the CFT side, there was this contribution containing delta H.
Yeah.
And are there any constraints on delta H, like positivity or some certain interval into which this has to be bounded in order not to violate unitarity or things like the quantum null energy condition or other convexity conditions? Or can it be an arbitrary number as long as it's not competing with C?
I think it can, yeah. So certainly what you would not want to do is have it, if it becomes order C, then if it had a negative sign, it could, shift the scaling dimension below the unitarity bound. That you would not want. But because, it's suppressed by 1 over C, if this is, minus 10 billion, I think,
okay.
I don't see any reason why that's,
okay.
Why that's not okay. Yeah,
okay,
so,
yeah,
and there would be a way to compensate for that in the bulk. It would be, again, a negative shift to the mass squared, but because it's suppressed by G Newton, it still doesn't violate the BF bounds. So, it's kind of the same thing. In both cases, it's like a very large, but 1 over C correction. So it seems to be, I don't see any reason to disallow that.
Okay.
Yeah, so I think it's unbounded at this stage.